So the main idea of this talk is I want to sort of talk about the meaning of Floer homology with respect to three manifolds. So when it comes to Heegaard Floer or instant Floer homology or monopole Floer homology, there are a few things we know about direct relationships between Floer homology and structures on the three manifolds. So for example, there's the Eliashberg-Thurston theorem combined with work of Ojbath and Szabo, and boosted by Kazez, Roberts, and Bowden to extend the result to the non-smooth case. Let's see. That a compact oriented three-manifold M. Okay, might as well say closed. Admits a co-oriented topolation. Then there exist contact structures which are deformations of this foliation. Such that the contact invariant well, let me put it this way. They are both non-zero the reduced Heegaard Floer homology. So let me say in minus plus, well no, plus minus R down here. Now this reduced part makes a difference. There's sort of, in each spin C structure, there's a particular class that that's sort of the reducible class. And that's where L-space classes land in. When you look at an L-space, it has one class in each spin C structure that's non-zero, and that's a reducible class. So having HF red be non-zero is an obstruction to being an L-space. And if you have some contact structure with filling with positive B2 plus, then you know that its contact invariant in Heegaard Floer lands in this reduced class, and so obstructs being an L space. So anyway, this is one kind of key example of a case where we have some structure in our manifold, and we get some structure in our Heegaard Floer homology that's a record of that. Of course, there's also just the contact invariant in general, but there it can be zero even if we have something that's tight. So there's not always a correspondence. You need to sort of specify exactly what kind of tightness you want before you know whether it's non-zero. Well, there are a few other things we know. So there's the adjunction inequality. So if sigma embeds in M, trivial handle, then of M in the spin C structure S vanishes the product with the, not the product, whatever, intersection product with the Turing class of the spin C structure is greater than the negative Euler characteristic. So that tells me something about the dual Thurston norm ball of my manifold. Now, so this is only relevant when have rational homology spheres, the Thurston norm ball is trivial, and so this doesn't really tell us much. So one could ask, well, what else does Heegaard Floer homology tell us? What does it tell us when we have a rational homology sphere, and what does it tell us about any other structures that might be related to our manifold? For example, how does it relate to the fundamental group? There's a conjecture that I'm sure a lot of you have already heard of before. I think Jonathan spoke about it at the school, and Jake mentioned it earlier, called the L-space conjecture. And that's one sort of strategy for looking at this problem, a kind of binary one. This would be sort of folklore. It was written down by Boyer, Gordon, and Watson. And Juhas wrote down another part. And I think also Osvath and Szabo had it mentioned not as a formal conjecture, but as something to think about in writing. Okay, so oriented, then the following equivalent. HF. And it's variation, and pi 1m it's a left order. And did Jonathan define these? Are we good with what top foliations are and everything? Okay, so oh yeah, okay, that's a good point. Prime, and this is actually, I mean, they all kind of it's prime kind of for stupid reasons, right? Like you're sort of each you have a foliation individually on each component, and you have left orders individually on each component. And unfortunately, the top foliations on each component nicely with each other. So, like if you replace this with the contact structure deformations, then they would play nicely with each other too, and it would just be something that glues together along S2s. But the top foliations don't glue along S2s. So this has to be prime for it to really be possible. So So do we know about this so far? Well, I guess we know about it for Seifert fibered spaces. We know about it for graph manifolds. We know about it for, I guess, what, strong L spaces. And Nathan Dunfield computations, and lots of other sort of random papers. You can also use tools from Seifert fibered spaces and graph manifolds to talk about satellites by algebraic knots or by torus knots. So for example, if you have a torus link satellite, then you get a space of L space Dane filling. So it looks kind of like this. And this also coincides with the space of non-left orderable fundamental groups and non-tot co-oriented foliations. Except for there's this little bit right in here that I can't prove matches up because of the fact that there's a non-trivial holonomy in the top foliation that you're trying to glue up. But otherwise, I have a theorem. If K is an algebraic link satellite of not whose surgeries satisfy the L space conjecture, then the satellites surgeries also satisfy them. Except for, well, so there's, yeah, this little corner here. Or if it has no, in the case that K has no L space surgeries, then besides the 3-sphere, then this just holds in general. Okay, so that's nice, but that question's getting a little bit old. So what's more interesting is to know, well, can we actually identify left orders with Heegaard Floer homology in a way similar to the Eliashberg-Thurston theorem, right? Where we have, here's my foliation, here's my Heegaard Floer class, this is where it came from. Or even in the case of foliations, you could ask the converse question, right? Here's my Heegaard Floer homology. Can you tell me which classes correspond to top foliation? So move on first towards that is looking a little bit closer at the Seifert fibered case. How do I write this? Let's see. Here, so for general theorem, Jake mentioned this earlier, And then there's sort of a alternative proof by Hansen and Watson. That given M compact oriented force boundary and more than one L-space Dane filling, the Heegaard Floer homology HF of M of alpha, where this is a Dane filling slope, is continuous, I'll say, complement of the pullback of this d tau set. So this lives in, so I guess I should say for alpha, dn. And this is the map induced by inclusion. So what do I mean by that? I mean, that's a kind of silly statement to make since the number of spin C structures is changing as you move along. But relative to that question, you know, of dealing with the spin C structure separately, you only pick up new classes or have changes in the gradings of your classes when you hit a slope coming from here. So for a ciphered fibered space, the tau is by so this is for M. So, and they'll say K runs from 1 through LCM of the alpha i's. So here I've sort of fixed an orientation for my ciphered fibered space. Anyway, I mean, this depends on conventions, but okay, so there's this, but if you match it up with results of, say, Caligari-Walker, and Jenkins. So M Okay, being filled along Bn plus 1. If and only if, say, oh, oops, there's, yeah. So this is a set here. So this is the rational longitude of my manifold. And I mean, so technically, it's true if this is true, or if you reverse the orientation and then you have a different, similar inequality. But every single time I get a new Heegaard Floer class, I get a new, and so a label which corresponds to the periodicity of the fiber under the corresponding homeomorphism that I use to construct the top foliation. And if so, so I also showed is a negative graph manifold, then the same, well, an analogous statement holds. Okay, so that's nice. So at least now we're seeing some correspondence between actual classes giving us foliations. I mean, you can also describe the transverse contact structures. This is the K is the maximal twisting number of the contact structure that's associated to these. But that still is a very special case because this is these are. Is that me? The Seifert fibered case and the graph manifold case those are ones where we sort of get the top foliation directly from the left order and vice versa. So what happens when we're in a more general case? Okay, so let me get my hypotheses right. All right, so definition. Okay, a total order on a version this is just an ad hoc term here. Version from the universal cover to R, which is pi 1 to m equivariant. So in the sense that, you know, in M and G. Okay, and so you can also define this as, well, here, let me get to that. Let me, where should I go next? I have to erase, that's no fun. Okay. So, a totally ordered foliation induced from total order speed. Right, so in other words, I have leaves given by so leaves of a foliation on the universal cover given by pre-images of points in X, and then these descend to leaves of a foliation on M. Okay. So, all right. Now a transverse left order is order on pi 1 of M with a dynamic action a fundamental group on R. The foliated R bundle holonomy rho over M has a transverse section. So what do I mean by that? I mean that kind of like a connection, like a flat connection, where you have a linear structure group. You can think of homeo of R as like a nonlinear vector bundle structure group. So the vector bit doesn't really happen, but it still specifies the holonomy of a bundle. So I've got some R bundle over my manifold M, and I can create this foliated bundle by starting with the universal cover of M. I mean, let's just call it hyperbolic or something so that it's say R3. And then I multiply that by R. And then I mod out by the action, so right action, given by rho on the real line and by deck transformations. Yeah. On the other side. I mean, I don't know how to say this. But it's a, I guess take it like this. Okay. And so this tells me when I have a leaf, if I go around some loop in the manifold, it tells me where I come back, kind of. So I have these loops, right? So I have this foliation, and it's not a product foliation, it's some crazy foliation of my manifold. And then the question that I'm asking is, do I have a transverse section? So can I find some global section? I mean, it's a trivial manifold, so I always have a global section, but can I find some global section, some inclusion of M into this bundle, such that it's transverse to the foliation everywhere? And if I have such a section, so then I call my left order, or if you prefer, rho. Order. Okay. So, theorem. There is a ejection. Totally ordered foliations and transverse left orders. So here I would say rho S, and this would be like 5. Yeah. So in the case that I can define a Heegaard Floer class that I associate to my left order, and it's just the one that I get from this foliation. So in particular, let's see, how much time do I have left? Okay, not too bad. You just All right, so there are three types of left orders. I'm never going to remember the author. So it's like Navas, and it's the authors of Groups, Orders, and Dynamics. Anyway, so there are three types of orders. So type 1, maximal. So a convex subgroup with respect to a left subgroup, which is convex with, you don't have anything smaller than it inside the group. So if this is a maximal convex subgroup, then this has, let's say this X translations on R. So the other two are action. Sorry. This. The action of G on R is a lift of an action on circle, and it's locally contracted. And 3 is everything else, which has a nicer description than I can read. Also have a conjecture that 3 only occurs as limit points. Never get one of type 3 unless you also have left orders of type 1 or type 2. So this first type includes all Conradian orders, and in particular, it's most of the left orders associated to manifolds with B1 greater than 0 have to be in type 1. So, where did I go? So, and I should also say, all these statements are like up to some extent. Actions on the real line, 2 left orders, and those are sort of well-defined up to semi-conjugacy. So when you you're sort of, you have what you want. Anyway, so I1, if is left order on, let's see, left order on M of type 1 and M modulo its maximal common subgroup has a transverse action on R. And so, this L gives me class C, which is equal to the ordered, well, the class that I would associate to the foliation, sorry, to the contact structure that's associated to the foliation that's associated to the transverse order. So here we get a situation that's a little bit like the analog of what happens with the Thurston norm and the adjunction inequality, except that I can't, this sort of covers the generic case for any left order on a manifold fundamental group with positive first Betti number. But in principle, you could also have a left order that's not of type on this manifold. So that's sort of like in, when you have a top foliation on a manifold with positive first Betti number, you could have something that doesn't have compact leaves. I mean, you could have just something that's got like, a bunch of, you could deform the leaves so you don't have these minimal surfaces in them. You can question if there's an adjunction type, well, maybe not adjunction, like what am I trying to say? So let me just write down the conjecture. And to make the conjecture well understood, I have to sort of say what I mean for a more general version of this. So this is what happens when you have transverse order. So let me say, remark. More generally, a transverse action R-order tree corresponds to a ordered foliation. And so given a left order on pi 1 m, attempt to deform this to an R-order tree action. And this also gives a class in Heegaard Floer. So and that would have a definite spin C structure as well. So conjecture, if that if class is well defined, then, well, okay, I guess I don't have to say it. So if that's well defined, then that would give me an obstruction on the spin C structures that I can associate to left orders. So maybe I should just call this for a mark. And this obstructs left orders on M via the adjunction inequality. So, and of course, if you could do this for types of left orders, then you could get a class for anything. But I wanted to make this point because it makes it, this is relevant even when you're not dealing with L space homology sphere. This is something that for manifolds with any Betti number, Hurst Betti number. So in principle, still associate these Floer to left orders even in the more in these higher first Betti number cases. That's all I had to say. So it depends on, so I mean, the most orders that you would associate to something in with positive first Betti number would be this type 1, and then yes, if you had a I mean, so I guess I should say any manifold with first Betti number that's positive has left orders of this type. Yeah. Okay, so the problem with this statement is that I don't know, well, first of all, whether such a thing can be constructed, and second of all, whether it would be unique. But, so you first section say, but now you have this R-order tree here. Preserved monotonicity, but I've forgotten part of my order, and I right, but So anyway, you could make a deformation of my total left order to a partial left order by changing my action on R to an action on an R. And every foliation has an R-order tree order for its leaf space. So, you know, if I find any R-order tree that has a transverse section associated to the holonomial I get from, I mean, I can still construct an R-order tree bundle over my manifold, right? And foliated by this R-order tree. And I can still ask to get a transverse section. And so if I get a transverse section, if I can find a deformed R-order tree that has a transverse section, that top foliation, which with a submersion on the leaf space to that R-order tree. And then I could associate a class in Heegaard Floer homology to that. But then, you know, so the two questions are, does each order admit such a deformation? And is it, you know, how